Look at this load test graph. As the simulated user traffic rises, the system violently cascades into a wall of 500 internal server errors. The instinct is to blame poor code quality. The actual failure point is structural. The engineering team split their application into smaller pieces, but they kept the tight coupling of their original design, creating a distributed monolith. Scaling a system is an exercise in rigorous isolation. You have to actively manage domain boundaries, decouple application state, and plan for inevitable network failures between services. This requires abandoning the comfort of strong, immediate data consistency across the board. To handle massive throughput, you have to embrace the complexity of eventual consistency. If you extract services without altering how they communicate, you inherit the rigid inflexibility of a monolith, multiplied by the latency and unreliability of a distributed network. We start with a standard minimum viable product. A single application handles the entire e-commerce lifecycle, orders, inventory, and payments, running on a single server and a single database. As the user base grows, the hardware hits its processing ceiling. Simultaneously, the development team expands. Dozens of engineers are stepping on each other's toes, blocked by merge conflicts and unified release cycles. To scale, we define strict logical boundaries called bounded contexts. The monolith divides into distinct domains: order, payment, and product services. Dividing code is useless if state remains unified. The non-negotiable rule is one database per microservice. Each gets isolated storage. Developers often try to shortcut this by querying across domains, using foreign keys to link the order table directly to the payment table. This shatters the model. Network boundaries must remain absolute. Instead, you build isolated domain entities. The order service maintains its own localized representation of the data it needs, completely ignorant of how the payment service structures its internal schemas. Strict database isolation guarantees that a heavy read query on the product catalog cannot lock the tables needed to process a payment. It is the prerequisite for deploying and scaling teams independently. With the domains isolated, the system faces its next stress test: a massive concurrent spike in user traffic during a flash sale. If these services communicate synchronously over HTTP, a bottleneck forms immediately. The order service calls the payment service and waits. The payment service calls the email service and waits. The entire chain is locked in a holding pattern. A synchronous command like rest-template.postForObject stops the executing thread completely until it receives a downstream response. Under heavy load, waiting threads pile up. The server exhausts its connection pool. Memory fills up, triggering cascading timeout failures. The architectural solution is to sever the temporal dependency using a message broker like Kafka. The order service creates the order, drops an event into the queue, and instantly returns a success response to the user. By switching to a non-blocking publish command, the executing thread is freed in milliseconds, ready to handle the next incoming user request without waiting on network latency. The downstream services consume those events at their own processing capacity. If the email service goes down, the messages wait safely in the queue until it comes back online. Decoupling services in time prevents localized slowdowns from destroying the user experience. Asynchronous messaging enables horizontal scaling. In a single database monolith, transaction management is built in. If an order placement fails midway through, a single database rollback command instantly erases the failed transaction, guaranteeing data integrity. Microservices destroy that safety net. A single user checkout now spans multiple, isolated databases, communicating over an unreliable network. Consider the standard checkout flow. The order is logged, but when the request reaches the payment service, the user's card is declined. This leaves behind a severe data anomaly. The order database holds an orphaned, unpaid order record that it currently considers valid. You no longer have a single database engine to lock rows and enforce ACID properties. You have to maintain data integrity across independent servers that might fail at any given millisecond. Resolving this requires implementing explicit communication patterns at the application level. You are forced to choose between prioritizing the strict accuracy of your data or the constant availability of your system. To enforce strict data consistency, engineers use the two-phase commit protocol. A central coordinator node messages participating databases to prepare for a transaction. The coordinator demands a vote to commit. Once confirmed, the coordinator locks every database simultaneously to apply updates. While those locks are held, the system's performance plummets. Any new requests hit a wall, making this protocol useless for high-traffic microservices. To bypass this bottleneck, microservices rely on the Saga design pattern. Here, there is no central coordinator and no global locks. Saga relies on eventual consistency. It breaks the global action down into a sequence of independent, local transactions linked by an event bus. To handle failures, Saga introduces the compensating transaction. If the payment fails, the system doesn't roll back a locked database. Instead, it fires an event backward, instructing the order service to execute a brand new action that deletes the initial record. This requires specific code implementation. An event consumer constantly listens for a payment failed event, which directly triggers a dedicated cancel order function. The responsibility for data integrity shifts entirely. Database rollbacks are no longer handled automatically by an SQL engine. They are custom application logic that must be manually authored and tested by the software engineers. Two-phase commit guarantees strict data accuracy at the cost of crippling your uptime. The Saga pattern secures massive scale and availability, but requires a severe increase in architectural complexity. This architecture diagram shows the fully evolved state: distinct domains logically isolated, scaled horizontally across servers, and communicating asynchronously through message brokers. Operating this machinery introduces a serious visibility problem. Tracking a single user's request as it jumps asynchronously across 10 different servers is impossible with standard server locks. This dashboard illustrates the solution. Identifying the exact point of failure requires implementing distributed tracing and centralized logging to aggregate metrics across every decentralized node. Furthermore, managing the deployment of dozens of moving parts requires automated continuous integration and delivery pipelines to eliminate human error during releases. Extracting code into microservices does not automatically yield scale. It is a calculated engineering trade-off. You solve hardware and organizational bottlenecks by adopting extreme structural complexity. Design your systems accordingly.